Good evening. We must begin with the transit of Mercury, which takes place on the 9th of May 2016. This is when the planet Mercury passes across the face of the Sun during a 7-hour period. It is visible entirely from here in the UK, Western Europe, Eastern North America, most of South America, and West Africa. Historically, it was the observation of the transits of Mercury and Venus and the fact that these planets show phases just like the Earth's moon, which helped shape the order of our solar system among the ancient Greeks. How this came about is a fascinating story. To the ancient Greeks, there was a mystery surrounding the Earth and the wandering stars seen in the night sky. To begin with, philosophers could only look out across the land all around them. The ancients believed that the Earth was flat, and that if you walked far enough, you would simply fall off the edge into an abyss. They also believed that the Earth was surrounded by a crystalline sphere of fixed stars. The first Greek philosopher to challenge this view was Eratosthenes of Syene, who lived around 276 BC. Eratosthenes managed to measure the size of the Earth. He was in charge of a vast library of books in Alexandria, and from one of these he learned that at noon on Midsummer's Day the sun is exactly overhead as seen from the town of Syene. This can be shown by the fact that at that moment its rays shine directly down to the bottom of a well. Here is a photograph of that well. Syene lies south of Alexandria. At the same moment, Eratosthenes found that from Alexandria the sun was 7.5 degrees from the zenith or overhead point. All he had to do was to measure the distance between Alexandria and Syene. A full circle contains 360 degrees, and 7.5 degrees is about 1/50th of 360, so that if the Earth is a globe, its circumference must be 50 times the distance between Alexandria and Syene. Eratosthenes worked out that the circumference of the Earth must be 24,850 miles. Eratosthenes was short of the mark. Nevertheless, from that moment, the Greeks realized that the sun, moon, and planets were in fact spherical bodies in space. As well as being a philosopher and mathematician, Eratosthenes invented geography. In his 3-volume work, Geography, which comes from the Greek word geographica, he described and mapped his entire known world, even divided the Earth into 5 climate zones, 2 freezing zones around the pole, 2 temperate zones, and a zone encompassing the equator and the tropics. Sadly, he was unable to work out why the Earth's climate became colder the further away an explorer travelled north from Alexandria, and warmer as he travelled south. Today we know that this great city lies at latitude 30 degrees north, so it is close to the Earth's equator. The Italian philosopher Philolaus, who lived in Croton in southern Italy around 470 BC, thought he had the answer. Philolaus suggested that at the centre of the spherical universe lay a central fire, around which the Earth, Sun, Moon and planets travelled in circular paths. The orbit of the Earth was supposed to lie in the plane of the equator, which of course helped to explain why no one had ever seen the central fire. Neither the Earth nor the Moon were believed to rotate on their axis, while Greece and the Mediterranean were claimed to lie on that side of the Earth, always turned away from the central fire. Philolaus proposed another planet travelled in a circular orbit lying between the central fire and that of the Earth. This extraplanet, known as the Antichathon or counter-Earth, performed three duties. First, its motion was such that it lay permanently between the Earth and the central fire. Secondly, it could help to account for eclipses, especially those occurring near the horizon. And thirdly, it made the number of bodies in the universe total 10, a number which had a great significance for all Pythagoreans who believed in the musical harmony of the motion of the planets. According to Philolaus, the orbital path of the Earth around the central fire was believed to take 24 hours, and therefore the apparent rotation of the stars was accounted for without having to transfer them any motion. Philolaus was the first to show a moving and spherically shaped Earth. Pythagoras of Samos, who lived around 570 BC, was an Ionian Greek philosopher who is often remembered as a great mathematician and scientist. He is best known for the Pythagorean theorem, which bears his name. You may have come across this while learning geometry at school. It states that in a right-angled triangle, the area of the square on the hypotenuse, that's the side opposite the right angle, is equal to the sum of the areas of the square of the other two sides. Pythagoras proposed that the sun, moon and planets all emit their own unique hum, or orbital resonance, based on their orbital revolution, and that the quality of life here on Earth reflects the tenor of the celestial sounds which lie physically imperceptible to the human ear. The Greeks believed that there was a musical relationship concerning the planets which became known as the music of the spheres, or harmony of the spheres. It is an ancient philosophical concept that regards proportions in the movements of the celestial bodies, the sun, moon and planets as a form of musica, the medieval Latin term for music. This music is not usually thought to be literally audible, but a harmonic and a mathematical or religious impression. The idea continued to appeal to thinkers about music until the end of the 17th century, influencing scholars of many kinds. The music of the spheres incorporates the principle that mathematical relationships express qualities or tones of energy which manifests in numbers, visual angles, shapes and sounds, all connected with a pattern of proportion. Pythagoras first identified that the pitch of a musical note is in proportion to the length of the string that produces it, and that intervals between the harmonious sound frequencies from simple numerical ratios. The planets all moved in magical perfect circles around a central globe. This was the essence of the music of the spheres, and this fascinated the Greek philosopher Ptolemy. We know virtually nothing about the life of Claudius Ptolemy. His great book, which has come down to us under the Arabic title of the Almagest, seems to have been written about 140 AD, and the date of the Ptolemy's death is usually given as AD 180. He spent much of his working life in Alexandria, where there was a great library. Ptolemy's star catalogue was based on that of Hipparchus, who lived around 190 BC, and he made notable advances as a geographer and a mathematician of the highest order. It was Ptolemy who drew up the first world map, which was based on scientific measurements rather than guesswork. The theory of the universe, as described in the Almagest, is always known as the Ptolemaic. Although Ptolemy himself did not invent it, He merely refined it and gave a comprehensive account of it. He had no patience with the absurd idea that the Earth might go around the Sun, and neither could he believe that the world is spinning round, because if the Earth were rotating beneath its atmosphere, there would be a constant howling gale. Therefore, he had to follow a system which could explain the various wanderings of the Sun, Moon and planets without allowing the Earth to shift at all. He was convinced that all paths of celestial bodies must be circular, since the circle is the perfect form, and nothing short of perfection can be allowed in the heavens. So Ptolemy accepted a plan involving what are known as epicycles and deferents, drawing upon the work not only of Hipparchus, who lived during Ptolemy's lifetime, but also of the earlier philosopher Apollonius of Cyrene, who lived in 4 BC. Ptolemy proposed that each planet moved in a circle around the Earth at a uniform rate. A planet cannot move across the sky in an irregular fashion if it is in a set, unchanging circular orbit around us, and Ptolemy was under no delusions. Of the naked eye planets, Mars, Jupiter and Saturn describe loops over periods of weeks. Mercury and Venus have their own way of behaving, but the wrong way or retrograde movements had to be accounted for somehow. According to the Ptolemaic theory, planets moved around the Earth in small circles or epicycles, the centre of which, the different itself, moved around the Earth in a perfect circle. Even this didn't do, and more complications had to be introduced. Under the Ptolemaic theory, the Earth was not only in the centre of the solar system, it was seen to be at the centre of the entire universe, because it was created by God Himself, and our world was therefore divine and perfect. Next in line was the Moon, Mercury, Venus, the Sun, Mars, Jupiter and Saturn, beyond which there was again the sphere of the fixed stars. The Ptolemaic theory was adopted by the Roman Catholic Church, who vigorously defended it against critics of the system who were seen to be blasphemous for criticizing God's divine work. Islam began in the early 7th century, originating in Mecca. It quickly spread to the Arabian Peninsula, and by the 8th century, the Islamic Empire was extended from Liberia in the west to the Indus River in the east. The Islamic Golden Age refers to the period traditionally dating from the 8th century to the 13th century, where much of the historical Islamic world was experiencing scientific, economic and cultural revolutions. They invented astrological instruments like the astrolabe. It was used by astronomers, navigators and astrologers by sighting the stars and planets through a sight across the instrument. It had many uses, including locating and predicting the positions of the sun, moon, planets and stars, determining local time, giving one's local latitude, surveying and triangulation. Therefore, the planets were now being scientifically observed and their movements plotted on early star charts for the first time. At first, the Arabs used the star catalogue in the Almagest. However, as time passed, they drew up catalogues of their own. They even built observatories which included various measuring devices that were put to good use. In the year 1270, King Alphonsus X of Castile called a number of Arab and Jewish astronomers to the city of Toledo and was responsible for the publication of the famous Alphonsine tables, the first known ephemeris which contained the data for predicting the positions of the planets as well as telling when eclipses of the moon and sun was due. Then, in 1420, Ulugh Bey, a Mongol prince, set up an elaborate observatory in his capital, Samarkand, and undertook a long program of accurate scientific work. His star catalogue was much better than Ptolemy's. Unfortunately for himself, he sent his eldest son into exile on astrological advice, with the result that the son rebelled and had Ulugh Bey murdered, bringing an end to the Arab school of astronomy. The observed movements of the outer planets by these early skywatchers proved problematic because they had some difficulty making sense of it all using the Ptolemaic theory. We now come to Nicholas Copernicus, who was born in the city of Torun on the banks of the river Vistula in Poland on the 19th of February 1473. He studied the situation carefully and published a book that eventually led to the demise of the Ptolemaic theory. The book was called De Revolutionibus Orbium Celestium, concerning the revolutions of the celestial bodies, and it proved to be a landmark in the history of science. This sacrilege did not appeal to the Church, which punished people severely for preaching against God's divine work. In 1600, Giordano Bruno was burnt at the stake in Rome, one of his crimes being that he taught the Copernican theory rather than the Ptolemaic. Fortunately for Copernicus, it was not completed until the end of his life, and the book was only presented to him on his deathbed on the 24th of May, 1543. Copernicus retained the perfect circles and continued to work with epicycles. However, he chose to place the Sun at the centre of the solar system and move the Earth out to the third orbit. Under the Copernican system, we have the central Sun, and in order of distance, the planets Mercury, Venus, Earth, Mars, Jupiter and Saturn, and again the whole is surrounded by a sphere of the fixed stars. At once, it appeared to solve the problem of the wandering stars, although the epicycles were complicating the mathematics and more were being added to resolve the matter. The term epicycle is derived from two Greek words, which in translation simply means upon a circle. It is really very descriptive, upon a circle. The term deferent is derived from the Latin defero, which means to carry, and their uses here will be obvious. The next advance came with the invention of a telescope in 1608, and the first skywatcher to use one was the Italian astronomer Galileo Galilei, who put it to good use. He made many improvements to this handheld refractor during the course of his lifetime, but it is his observations that have proved important. He observed sunspots for the first time by projecting an image of the sun's disk onto a white wall. He observed the craters and seas of the moon and the phases of Venus. Galileo had found a flaw in the Ptolemaic theory. The planets Mercury and Venus would not show any phases at all if they were beyond the Earth's orbit. Only if the planets were inside with the Sun at the centre of the solar system could this be accounted for. This was strong evidence in favour of the Copernican theory. Yet, he had to be very careful in what he wrote in his published books, like The Starry Messenger, and how he taught his pupils. In the end, the matter was investigated by the Roman Catholic Church's Inquisition in 1615, and they concluded that it could only be supported as a possibility, not as an established fact. Galileo later defended his views in his book Dialogue Concerning the Two Chief World Systems. This work appeared to attack Pope Urban VIII, and this alienated Galileo and the Jesuit priests who had supported him up until this time. He was tried by the Inquisition. He was found vehemently suspect of heresy. He was forced to withdraw his views, and then he spent the rest of his life under house arrest. Galileo died on the 8th of January 1642. This brings us to the next advance, which came with the observations of a Danish astronomer, Tycho Brahe, who was born in 1546. He was not a supporter of the Copernican system and stubbornly maintained that the sun moved around the Earth. However, he made a great many accurate observations of star positions and also measured the movements of the wandering stars, particularly Mars, which proves to be useful to his last assistant, a young German named Johannes Kepler. In March 1591, Mars was in the zodiacal constellation of Sagittarius, the Archer, and over the next 7 months, Mars appeared to perform a loop among the stars, which ended in October of that year, something which interested Johannes Kepler as a mathematician. When Tycho Brahe died in 1601, his observations were passed on to Kepler, who made great use of them. Kepler started with the assumption that the sun lies in the center of the solar system. He then did his best to work out a theory which would suit Tycho's observations. He concentrated upon Mars and toiled away for several years, only to meet with failure after failure. The observations nearly fitted, but not quite. Either Tycho's work was inaccurate, or else there was something wrong with the theory. Kepler had great faith in Tycho as an observer, and at last he found the cause of the problem. The planets do indeed move around the sun, but they do so in orbits which are elliptical rather than circular. One way to draw an ellipse is to stick 2 pins into a board, a centimetre or 2 apart, and join them with a thread, leaving a certain amount of slack. Now draw the thread tied with a pencil and trace a curve. The result will be an ellipse, with 2 pins marking the foci. If the pins are wider apart, the same length of thread is used, the ellipse will be longer and narrower. The distance between the foci is thus a measure of the eccentricity of the ellipse. Once he had taken this decisive step, Kepler was able to draw out 3 fundamental laws of planetary motion. The first states that a planet moves around the sun in an ellipse with the sun at one of the focuses. The 2 terms perihelion and aphelion were introduced to note the points when a specific planet was close to the sun, perihelion, or farthest away from the sun, aphelion, as it moves around its orbital path. The third law gives a relationship between a planet's time of revolution, the sidereal period, and its distance from the sun. So the planet Mars moves along its orbital path at a slower speed than the Earth, and the same is true of Jupiter and Saturn. The orbital velocity of the Earth is 18.5 miles a second, and that of Mars is 15 miles a second, while that of Jupiter and Saturn is 8 and 6 miles a second, respectively. The observed wandering loops of the outer planets among the constellations could now be explained quite easily. As the Earth moves around its orbital path, it takes time to catch up Mars, which is further out, and moving along more slowly. The Earth then catches up Mars because it is the faster of the two planets, and finally Mars lags behind the Earth because our planet is the quicker of the two worlds. The other difficulty was that the superior planets, Mars, Jupiter and Saturn, do not show significant phases like the Moon as seen through a telescope because they are beyond the orbit of the Earth. Two of the planets, Mercury and Venus, are closer to the Sun than we are, so that they have their own way of behaving. They are sometimes termed the inferior planets. To begin with, we can never see them against a dark background, except when they are low down in the sky. They always lie in roughly the same direction as the Sun, and are at their brightest when in the west after sunset, or in the east before sunrise. Importantly, they show phases similar to those of the Moon. The first recorded transit of Mercury took place on the 7th of November 1631. In a paper published at Leipzig in 1629, Johannes Kepler notified astronomers that according to his calculations, a transit must occur on this day, since at the time of conjunction he had found the latitude of Mercury by his tables less than the Sun's semi-diameter. Kepler's prediction was verified by Paris Gassendi at Paris. It proved beyond doubt that Copernicus was indeed correct. It was this fact that gave the Copernican system great emphasis and support among the earlier observational astronomers who were able to use the first telescopes to see the phases of Mercury and Venus. The second observation of a transit of Mercury was made by Jeremiah Sharkley on the morning of the 3rd of November 1651 in the East Indies. The angular separation between Mercury and the Sun in the sky is never as much as 30 degrees, and it never rises long before the Sun or sets long after it. Also, it is a small world, not a great deal larger than the Moon, and as the phase increases, the apparent diameter shrinks, because Mercury is drawing away from the Earth. City dwellers will probably never see it with the naked eye, though people who live in the country may see it shining as a fairly bright star-like point when it is best placed. The movements of the planets can now be explained with little difficulty thanks to the mathematical genius of Johannes Kepler. When the planet Uranus was discovered in 1781, it fitted nicely into the framework, and the next planet, Neptune, was discovered in 1846, became the 8th planet in order of distance from the Sun. The dwarf planet Pluto, the most distant, was discovered by the American astronomer Clyde Tombaugh in 1930, and there may well be others waiting to be discovered. Like Mercury, Venus can also transit across the face of the Sun, although not very often. This last happened in 2012, and the next is not due until December 2117. So, do make the extra effort to join members of your local astronomical society, and in Kosovo, please join Pranvera Hajzeni and her team to safely see the transit of Mercury. It is a wonderful event to watch. It makes a nice photo opportunity, and of course it is of historical importance. I would like to thank the European Southern Observatory and the European Space Agencies and Hubble Science teams for sending me further educational material and for all their valuable help in the making of astronomy and space. It is greatly appreciated. that is all we have time for this month. Please visit our website, Astronomy and Space Blogspot, where you can see all of our past shows. And if you like this program, please share it with your friends and members of your local astronomical society. Until we come back next month, stay safe and thank you for watching.